In part C, we're asked to find x of 4, and since we're given dx dt, we really want to integrate the derivative of the x-coordinate with respect to time to get the position, the x position at time t equals 4, or the x-coordinate of the position at time t equals 4. So we set it up this way. Now with these kinds of problems, it's very important to note that you do have, at time t equals 0, you do have the position of the object. That's at -3, -4. And since you have the position of the object at time t equals 0, and you're looking for it at time t equals 4, you can say something like the integral from 0 to 4 of x prime of t dt, which is our dx dt in this case, is equal to the antiderivative of x prime of t, which is just x of t, evaluated at the upper limit, which is 4, minus the antiderivative of x prime of t, which again is x of t, evaluated at time t equals 0, or the lower limit of integration. Now, this is just the fundamental theorem of calculus, and since this is a calculator problem, we can calculate the left side of that equation, and we know what x of 0 is. X of 0 is -3. And then we can solve for x of 4, and we have our answer there. So I'm going to bring the calculator back in, and you recall that dx dt is equal to the arctangent. So I'm going to go back to my y equals screen, and that is y1 is my dx dt. So I'm going to turn off the speed function, turn on dx dt. I'm going to zoom standard, and what I'm looking for then is the integral from 0 to 4 of that. So second calc, 7, lower limit 0, upper limit 4, and I get 2.108 rounded to 3 decimal places. So all that's left now is to solve for x of 4, and since x of 4 plus 3 is the right side, we're going to subtract 3 from both sides. And so x of 4 is equal to 2.108 minus 3. We'll use the calculator again and go to the home screen. 2.108 minus 3 is equal to -0.892. And so we end up with x of 4 being equal to -0.892. Again, this is by use of the fundamental theorem of calculus, and hopefully that's clear how we went about doing that. We'll go on to part D. And we're told that there is a point on the curve where the line tangent to the curve has a slope of 2. If you recall that the tangent to the curve the tangent to a parametric curve is given by dy dx is equal to dy dt over dx dt, and we're told that at some point this has a slope of 2. So this time we're going to graph that slope curve and find out where it's equal to 2. So we bring the calculator back in, we go to y equals. This time we want y sub 2 over y sub 1. So we'll turn off y sub 1, and we want vars, y vars, function y2 divided by vars, y vars, function y1. We get y2 over y1. I'm going to zoom standard, graph that, and I want to find out where it's equal to 2. So I go back to y equals, and I plug in the curve y is equal to 2. I graph, and I'm looking for the intersection there. First curve, the second curve, and I get close to the intersection, and that gives me the intersection is when t is equal to 1.3576631. Now I want to find the acceleration vector at that point. And that means I want dx dt and dy dt at that value, so I turn those on and everything else off. I'll continue this in the next video.